Rayleigh distribution and methods of calculating the significant height of waves from wave spectra, or from wave records. We talked about one generation of waves and discussed the fetch limiting and duration limiting aspects of wave generation. And then we began talking about the initiation of movement of sand by waves. Today I'd like to talk a little bit more about sand movement by wave. You take one of each of those. And then talk about sediment transport on beaches, and then suspension of mud by waves. So our first concern will be transport on beaches. I said that when waves approach a beach at an angle, they refract onto the beach, but still at an angle. They run up on the beach and back down, and it's the sawtooth pattern of their motion that creates a long-shore current. The current transports the material, but it's put into suspension by the breaking waves. That is, as the waves break onto the bed. You can stand on shore and see that process. The water is turbid out to some distance from shore as the waves suspended. It's particularly apparent from the air or from up on a cliff if you look down on the water. There's presently considerable effort in trying to develop models of longshore transport. They're all pretty much in the experimental stage. That is, there isn't anything that I know of anyway that can be used for design. What the Shore Protection Manual describes, and what's commonly used everywhere, is the empirical relation between power, wave power, which is what suspends what's dissipated when the wave breaks, and alongshore transport. You can describe the average power as being equal to the wave energy times, or as being equal to the wave energy flux on shore. And the flux which is gamma h squared, and I'll leave it at that, divided by 8 times the celerity of the group of waves coming on shore. That is, it's the energy, and this is the energy flux through a plane perpendicular to the path of the waves. That is, if we have shore contours like this, and the waves are coming at an angle like this, then this is the energy passing through a plane perpendicular to the direction of the waves. Okay. And of course, on shore, as they approach shore, the waves are refracted. So the angle on the shore is something different than the angle in deeper water. Well, let's call this angle relative to the shore alpha. And remember that we said that the group velocity of a collection of waves approach the celerity of the individual waves as it comes on the shallow water. So this is very closely equal to gamma h squared over 8 times the celerity on shore. The energy per unit width of each And this is energy per unit width of wave, right? Per unit length of wave crest. The energy per unit width of beach, let's say 1 foot or 1 meter, is equal to the P, I'll write it down here, energy per is equal to P bar cosine alpha, which is equal to gamma h squared over 8 cosine alpha, C times cosine alpha. And the longshore component is just equal to P bar cosine alpha sine alpha. And that's cosine alpha sine alpha is equal to half sine 2 alpha, remember from trigonometry. So we can write the longshore component at the beach. They're at the beach, so this would be H sub B here, is equal to gamma H squared over 16 sine 2 alpha. And if we use the significant wave height, then we can write, just as we have down there, the P longshore at the beach is equal to gamma H squared, significant H squared over 16. This is alpha at the beach. And I walked off and left over at the civil engineering office the graphs that show the relation between that and sediment transport. So rather than break up our time now, I'll draw up for you a description of that, and then we'll discuss it on Monday. What it is, it's a log of P bar longshore transport against log of longshore transport in meters cubed per year or a day or whatever, and also in yards. It's on the log scale, and it's about three orders of magnitude on each side, and the data plot as a nearly straight line with about a plus or minus 50% range on either side. Now, before we go on, I'll have to tell you how these data are obtained. They also have some graphs showing the deep water wave conditions against longshore transport for a straight beach, or just a straight beach like that. What's done is to look at the accumulation of sediment near groins or near any kind of obstruction. For example, a tombola. Along the California coast, we occasionally have a big rock offshore, some kind, called a tombola. And the sediment that's transported along the beach accumulates in this region. And in fact, if it keeps accumulating and getting high enough, and if there's some wind there, then it actually migrates on shore and makes very large deposits. Bodega Dunes State Park, you get a chance to go over there and take a look at it. It's all sand dunes that have been washed on shore by the local tombola. There's, in any case, either that or some kind of an obstruction. A jetty, for example, offshore will accumulate sediment, and by measuring the change in volume and taking the wave data from upshore during a year and calculating for each storm, each series of waves, what the transport was. And typically it'll be transported one direction part of the time and in a dominant direction the rest of the time. Calculating what the transport is, then they can find a relation between these two. I'm sorry, calculating what the longshore energy flux is.
Is the transport on land by wind significant in those areas?
Up here?
Yeah.
By wind.
Yeah.
That's brought on shore by wind. Just when the tide goes out and the sand dries, then the wind can carry it on shore. An example of this is the breakwater at Santa Barbara. Santa Barbara is, well, actually, down the coast quite a ways. The coast of California goes out to a point like this, and then it goes in and down. Santa Barbara is about here. They built a breakwater, not here, a breakwater to protect small boats from waves coming in on shore. And they found that in a short time, sand accumulated in a kind of a fillet here, and then more sand accumulated, and finally accumulated clear out to the end, and it was transported along the end and then accumulated in here and blocked the entrance to their harbor. Not only that, but there were some resort hotels over here, and the sand beach that they used to have began to disappear. And pretty soon the water was right up at the front door of the hotel. So they, and in fact now there's a high school here and a track and football field and so on, all out on the sand. But in any case, the alarm sounded when the shore began to disappear here, and they established a pumping station here, and they pump sand over to this beach. So the sand that comes down the coast now comes to this point and is pumped across over here. It's a sand bypassing operation. Not an uncommon problem. In fact, the Corps has had research on sand bypassing as long as I can remember. And there aren't any really satisfactory answers because it keeps coming, you know, year in, year out. I'll tell you one other story and then we'll go on. Transport. The little town of Santa Cruz, west of San Jose here, wanted a yacht harbor, and they persuaded their congressman to fund the Corps of Engineers for a feasibility study for a yacht harbor. There was a little inlet there. They wanted a yacht harbor built in inlet, and the San Francisco district of the Corps did a feasibility study, and they found that it wasn't feasible. And they reported that to their congressman, And he said, well, we want a yacht harbor there anyway. People wanted a yacht harbor. They weren't willing to accept that. And the Corps can do anything, you know. So the Corps designed a yacht harbor and said, you know, this is going to be a problem. The problem was that just a few hundred yards up the coast, on the mouth of the San Lorenzo River came out. And it just discharges quite a lot of sediment there, and that sediment's washed down past this harbor. Well, within the first I'd say, 2 or 3 years after the harbor was completed, that people complained that the entrance to the harbor filled up with sand. And recorded and do a good job of designing it. That's, they were in a position where they couldn't win. So they brought out an experimental sand bypassing operation. They had just a couple of jetties coming out in the ocean. Experimental sand bypassing operation. And it worked mechanically, but it couldn't keep up. There's about 300,000 cubic yards a year going past that harbor. And it didn't come uniformly through the year. It came in big pulses when the San Lorenzo River had high flows. So that during these pulses, the equipment just couldn't possibly keep up. In fact, it would take huge equipment to do that. I was involved in a study with the Corps shortly after that, and it turned out that because it comes in huge pulses, if they would allow it to just shoal in for a couple of weeks each year and dredge out those huge pulses, the rest of the year it'd stay open. So that's what they're now doing. So just to give you some idea of the nature of these ends. Well, this is purely empirical, and it's plus or minus 50%. And often, because the sand, you calculate sand transport in one direction part of the time and another direction the other part of the time, depending on where the storm is out in the Pacific, you're taking the difference between two large numbers, which means that the numbers aren't very reliable. If you get involved in coastal engineering very much, you'll find that at almost every entrance where there's some kind of a problem, you'll find a group of people that say the sand is moving this way, the dominant motion is this way. You'll find another group of people that say the dominant motion is this way, and they won't speak to each other. I mean, they usually have firm, strong opinions. Of course, I don't have strong opinions. But they do. And the reason is because of this taking differences of large numbers. Now, the other point I want to make is that when rivers discharge a large amount of sand onto the beach, the longshore transport, which normally continues along the beach, can't cope with it all. So it piles up there for a while until it gets smoothed out again. And as a result, the river mouth will move north. That is, it'll pile up sand so that in order for the river to get around it, it'll move north. And if you go down the coast of California, you'll find that the rivers all come out at the north side of their valleys. Quite interesting. They've all moved over to allow their sediment to accumulate. The source of sand is not just rivers, however. Part of it's erosion of the beaches, the cliffs on shore, and along California, that's particularly a problem. And in some areas, the exposed geologic formations near shore have yielded materials. There's a beach. I haven't mentioned this, but beaches tend to be steeper if the particles are coarser. That coarser particles make steeper beaches. And the reason for that is that coarse material isn't as easily eroded as fine material. But when it's on a slope, on a steep slope, gravity aids in its erosion. That is, it's moved more easily on a slope than on a steep slope than a flatter slope. There's a slope down north of San Diego, or a beach down north of San Diego that's made of rocks 4 or 5 inches in diameter, well-rounded rocks 4 or 5 inches in diameter, and the slope is about 1-on-1. I mean, it looks like a levee, but it's not. It's rocks that have been moved there by wave action. And in fact, when the wave action is strong during storm periods, the rocks growl. You know, you can hear them rubbing against each other. I talked to Professor Inman at Scripps about that rock situation. It's at the mouth of a little lagoon called Vataquitas Lagoon. Forgot the name of the town near there. And the Port of Los Angeles is going to rehabilitate Vataquillas Lagoon. It's full of mud now. To dredge it out and make it back into a biologically active, you know, bird type, fish type habitat. And there was a lot of controversy about how it was to be refurbished. Bird watchers have different ideas than the rest of us. You know, they want certain things, and other conservation people and environmental people want different things. And there was some argument about how this was to be done, how it was refurbished, and I was asked to go down and review the plan. And I went out to this beach of cobbles out there and looked at it, and it was very impressive to me. You know, I had never seen a beach like that. Great big rocks, obviously placed there by waves and obviously subject to motion. And I looked at the plans they had, and they planned to have a 200-foot wide opening without jetties going out into the water. In fact, one of the conservation groups insisted that there be no jetties out on the water. Well, those rocks would have filled up that 200-foot, would have moved laterally by the processes we were just discussing in a year or two. You know, so the question was, they either had to put jetties or plan some kind of a maintenance program to keep it open. Well, I really got into it with that one. The people that designed the plan said, "Oh no, those rocks aren't going to move, they're too big." Then I went down and talked to Professor Inman, and I said, "Doug, those rocks must move." He says they move at about 10% the rate of fine sand, which is appreciable. You know, fine sand moves maybe a mile a year. Particles, well, 10% of that's 500 feet. You know. Well, part of the problem, I guess that illustrates, is that there's an awful lot we don't know about beaches, you know, sand movement on beaches. And the basic difficulty is describing the hydraulics, describing what happens in a breaking wave. Well, this energy approach is one that's widely used, and I think it'll be used for some time in the future. Well, I'd like to turn now to the matter of cohesive sediments. That's what this is all about. Well, recall we were talking about shallow water waves and the fact that the orbital pattern was something like this. And just back and forth near the bed. Now, when I say near the bed, we'll call that the velocity use of V. Near the bed, that's really at the top of the viscous layer in a smooth bed, hydraulically smooth bed. We have a way of describing the maximum velocity. Recall for the velocity in the x direction, we have the phi h and t times the hyperbolic cosine of phi v plus v over L divided by the hyperbolic sine 2 pi v over L. Times sine cosine of 2 pi x over L minus t over the period. And the bottom, at the bottom, this term, where d equals minus z, this term is 0, so the hyperbolic cosine is 1. And the maximum velocity, we want the maximum, occurs when this term is plus or minus 1. Right. So we just have pi h over t times 1 over the hyperbolic sine 2 pi u over L. So we know the maximum velocity that will occur on the bed, and it goes from 0 to that velocity and then back to 0 and reverses back and forth. So the absolute velocity is equal to this with the other sign. So we can say then that the shear stress on the bed, we'll call it tau 0, what we've been calling it before, is equal to a factor times rho u sub b squared over 2. We've been calling this in, when you're dealing with average current, we've been calling it C sub d, remember? Well, I'll put F sub w for the friction factor under waves. I passed out to you a few pages from Keith Dyer's book. Looks like this. That you can read the wave boundary layer section there. And he points out the several methods of refining F sub w from the Reynolds number. When it's hydraulically smooth, and the bed is hydraulically smooth, you can write that F sub w is equal to 2 times the Reynolds number minus 1/2 power. This is dimensionless, and of course that's dimensionless. And our appropriate Reynolds number is the maximum velocity times the excursion. Excursion is this distance here. U sub b times excursion. We've been calling it x. I'll call it x0 or x w, and divided by the kinematic viscosity. And we have for x sub w by the same route of reasoning is equal to the height of the wave divided by 2 times 1 over the hyperbolic sine of 2 pi d over L. This gives the excursion from the center to the outside, and the 2 up here is to give the full length of the motion.
Could you give the reference for that again?
What's that?
The reference for this?
Reference?
Yeah.
Keith Dyer, D-Y-E-R.
What's the name of the book?
It's called Coastal and Estuarine Sediment Dynamics. Keith R. Dyer, D-Y-E-R. By John Wiley. Here, I'll write it on the board. And it's John Wiley, April 9th, well, the original date was 1986. We started in 1990. It's a good book, but it doesn't go into the background of any of these things.
I have a question. On the equation here, they use
Yeah, that's what I called X of W.
All right.
I think he defines it on the previous page.
No.
Well, maybe not.
Something missing here.
Maybe we're missing something.
Right at the bottom of the page. Yeah, I think a sentence.
It starts in the middle, I believe.
On the next page, there's a plot showing the hydraulically smooth and turbulent conditions. If you have on the right, there's a scale, this A, which I call X of W. Why don't I call it the same thing he did? Boy, it's confusing here. A sub B or KS. And this is the Nicarazzi roughness. Y'all find that figure?
I think we're missing a page somewhere.
I think that maybe we're just missing a sentence at the bottom, right?
This figure here.
Yeah. 97 and 100.
There's two, they don't all go together, there's two sections, I'll talk about the other one in just a minute. One deals with tides and the other deals with waves.
Right.
Okay, do you all find that figure? That's just like the, the diagram you used for pipe rough.
Moody.
What's it called?
Moody.
Moody diagram, right?
Moody diagram.
What's that?
Moody.
Moody.
Moody?
M-O-O-D-Y, a Moody diagram for Reynolds number?
That's not right.
Yeah, that's right.
There's a diagram just like that for pipe roughness. It's called, well, it'll come to me. Where you deal with relative roughness. Well, there remains a problem, and that is, suppose that you have currents and wave action. Typically, well, when you have a current, at least in the boundary layer, you can say that the shear stress due to a current is equal to rho u star squared. But it will have some direction. Let's say and then there'll be a shear stress due to wave action, which will have some other direction. And of course, the resulting shear stress of the two, you expect to be the vector sum of those two. The actual value, I don't know if I have quite the scale. However, will be a little bit higher than that. And the reason is that the wave orbital motion of the waves, under the waves, enhance the mixing, the momentum transport that we talked about before, you know, the interchange, so that the effect of the waves is to either slow the current or, for a given current, to increase the momentum transport. However, in most circumstances, in shallow bays anyway, the currents are so small compared, the current stress are so small compared to the waves that you normally just neglect them. You just consider the wave. Shallow bays tend to fill and empty with some circulation. Sometimes it goes like this and back out, or sometimes it just flows around through the bay, but it's generally quite slow in shallow areas. Not so in channels, but then wave action is no problem in channels either. I gave you a reference, I'll give you a reference to a study done in Lake Balaton in Hungary, where they neglected currents and discussed the relative value. There's one other thing about suspension by waves. Well, first of all, if you notice the shear stress due to waves, then presumably you can apply that to the rate of erosion, which is equal to the shear stress divided by a critical shear stress for erosion. Provided that you know the critical shear stress for erosion. And remember that changes with depth. In the flume studies report, it shows penetrometer measurements that show that the physical resistance to the penetration changed with depth, and that this change migrated upward with time. That is, at early time it was something like this, and at a later time it was like this, and finally it was just a gel. So that depending on what the bed profile looks like, it may be that the material, and this is surface erosion. So the material may erode more and more slowly with distance down. There's also a handout discussed, should have been discussed in the videotape, describing Meta and Parcher's measurements showing changes in bed shear stress, critical shear stress with depth. This is for surface erosion. If the shear stress exceeds the bulk strength of the material, however, it'll just erode immediately down to the depth where that strength equals the applied stress. So typically what happens is that if the material is freshly deposited so that it has some kind of a profile like this, then it's easily resuspended by bulk erosion. If there's a long time between the time it's deposited and the time it's subject to wave action, then it isn't easily suspended by erosion, and a different process takes place. In the videotape, did it show some slides describing a wind tunnel where the waves went over, wind was passed over shallow water and the waves suspended the material? That wasn't in the videotape? Okay, Monday I'll show you that. A case of bulk erosion. In many estuaries like ours here at San Francisco Bay, sediments come in a very short period of time, maybe 10% of the year or less, and deposit in the shallow bays and then are resuspended by wind later. Those sediments are freshly deposited and easily resuspended. If they're allowed to stay for a time, then they're not easily resuspended. And that appears when you look at multi-year accumulations of sediment not being resuspended and it accumulates. But typically the material comes and deposited in shallow bays, and then during the year it's suspended day after day after day, so it never has a chance to really consolidate or gel, and it's easily resuspended and transported onward. I'll show you that Monday. If the material forms a gel, becomes sort of a uniform gelatinous material, Then a different process takes place from what we described here, surface erosion or bulk erosion. What happens is that the material is viscoelastic and it deforms under the wave. As the bed moves, say this is the bed, as the shear stress on the top goes back and forth, what you see is that the bed itself goes back and forth. In fact, it goes in a kind of in a slightly, this won't be just back and forth as the bed yields, it'll be something like this. And the bed will form a smaller one, something like that. I once put mud in a flume and put little dime store pearls next to the glass, and you could actually see them as the wave went by. You could see the pearl moving under the mud. If you increase the amplitude of the wave or steepness, what you'll find is that this grows and grows, and then pretty soon the deformation of the mud destroys the structure of the gel, and it fluidizes, and you get a layer of turbid water above it. It usually has quite a sharp interface, in fact. A turbid water above it, it just fluidizes it. Not erosion in the normal sense of the word. Although it does eat away at the surface, it makes it soft and very easily suspended. I passed out a paper. The paper by Foda, Hunt, and Chow describes that process. It's a 1993 paper. And it provides a theory that explains this deformation. So we have those three processes. One, surface erosion. Two, bulk erosion, where the surface fails to some depth. And then three, this fluidization process. Sounds complicated, and I wish we had a better way of predicting what the strength of it was as a function of depth. The problem is it changes with time, so you have some difficulty. Well, that's all I plan to say about waves. What I'd like to turn to next is tides. Tides are generated by the attraction of the sun and the moon and other stars. And their attraction is kind of interesting. The moon, the axis of the moon is tilted in an angle of, I think, 23 degrees to the axis of the Earth, or the plane of the Earth's rotation about the sun. And of course the sun is much, much further away from the Earth than the moon. The moon's axis precesses, moon's plane of rotation, I should say, precesses around the Earth with a period of 18.6 years. And of course the sun goes around, the moon goes around the sun 365.25 days. The attraction of the gravitational attraction of the moon to the Earth results in a two-body rotation that's actually like this. That is, they're rotating about some common center, the two of them. And of course, the Earth and Sun are also. But the attraction of the Moon to the Earth causes the water to flow toward the attraction. So the water is higher on the side of the that the Moon is on. And of course, the fact that they're rotating about each other produces a centrifugal force on the opposite side. So there's actually a bulge on the far side at the same time. Because the Moon is closer to this side, the bulge on this side is greater than the bulge on this side. But they're both comparable bulges. Now the Sun also attracts the water on that side and this side, but because it's so far away, the attraction is much smaller. Remember, the force of gravity is proportional to 1 over the distance squared, according to Newton's law. And because it's so far away, the attraction is less, but it's still significant. When the Sun and the Moon are lined up, more or less lined up, then we have strong attractions, some of the two. When they're at right angles to one another, then we have each of them separately and sort of spreads it out. And when they're just directly opposite each other, then we have high again, but not quite so high as when they're both on the same side. So you can see that the astronomical forces generate the tides, and if the Earth were just a ball covered with water, it would look just like that. But the fact is it isn't. It's got continents, and the continents are sort of strung out north to south, so that we have ocean basins. And this wave, which progresses at well, let's say it in a 24-hour, has a 24-hour period going around, half of this 12.5-hour period going around this. That's a long period, and relative to the depth of the ocean, we're talking about a shallow water wave. You know, this wave travels around, but because its period is so long and its wavelength is so long, compared to the depth of the ocean, it's really a shallow water wave. And when it meets the continent, a continent or some kind of a shore, then it's reflected, complicating the waves. And when the time it takes a wave to go from one side of an ocean basin to the other is some even multiple of 12.5 hours, 12.4 hours, then there's a reflection that's in phase, and you get an amplification of the tides. That is, you get resonance, and the tides at either end will be high, and then the center will be low, and that's what you find. At the mouth of the Mississippi River, for example, which is in the middle of one of those, the range of the tide is about 18 inches. You know, very little tide. On the other hand, in Baja California, or at one end of the straits between England and the continent, the tides are like 30 feet, you know, 10 meters or so. All because of this resonance that you see. Well, the complications of the resonances, the friction of this fact that it's a shallow water wave, and so the bed friction, even in the deep ocean, is significant. And the complex configurations that we have in estuaries, the tides become very complicated. The method of determining the tides is, first of all, to establish a network of base stations. And one base station is at the Golden Gate Bridge, the Presidio station. That's the one we use here. And then in an estuary, something like this. This is San Francisco. you can see that we have complicated shapes, and not only is the tide, if the surface of the ocean rises out here, then water flows in through the Golden Gate and it fills up this basin, but because of the restriction here, water has to rise in here before it really begins to flow through here. So the tide wave progresses from one basin to the next. There are actually more basins up here, and the delta and so on. And similarly, down in South Bay. The tide at Martinez is about 2 hours after the tide at the Golden Gate. Quite a lot of delay. And not only that, I didn't draw the channels in, but the flow from the channels, there's a channel going across here and a channel going down here. There's flow out of the channels and back into the channels during the reverse of the tide, which also causes some delay in tide stations. So if you have a tide station here and a tide station here, you'll find that they have peaks, high tides at different times, and low tides at different times. The water flows, rises and falls in the ocean, but it flows back and forth inside the estuary to fill it up, as necessary to make the tide rise and fall in various parts of the estuary. So we have a situation where there's just a tide out here, but flows inside, and the flows are reversing, of course. That's because the tides rise and fall. In the San Francisco Bay system, it's resonant between here and here, with the result that the amplitude of the tide, the base station is here. The amplitude of the tide down here is about, the range of the tide, down here is about 2 feet greater than it is at the Golden Gate, just because of this resonance inside the system. We can see that the tides are complicated. It's not easy to describe the tides. So what's been done is to establish a base station in each area. There's one near Seattle and so on. And they have long records. The record for this one began in about 1848, if I remember correctly. Then periodically they'll put temporary stations in various places. There's a river going up here. In various places in the system, and leave them there for typically about a year. And then they can relate the tides at each of these base stations to this one and produce tables like the ones I passed out to you. You can see that the table is the table of the tides, highs and low tides at the Presidio, Golden Gate. Then on following pages, they have tables that give the position of the other temporary station, then the differences in highs and lows elevations, and first two are time in hours and minutes, and then differences in high water and low water elevations, so that you can take the tide at the Golden Gate and then apply these factors to get the tide, high and low water tides at other locations in the bay system. This is for San Francisco, but you find the same thing throughout the United States. Now there's more to it than that. These are predicted tides. And the predictions are made on the basis of Fourier and Ellen, or Fourier series. And the handout that I gave you from Dyer has on page 90, I hope it has all of them, principal tidal constituent. And they've been given these symbols, M1, S2, and so on, the moon and sun I forgot what K is for. And what they are is that it's in the moon, case of the moon, well, it's 12.42 is the moon value. What they are is the tidal period and the tide, I'll call it tide, is calculated as a Fourier series, an amplitude times the sine of 2 pi times t time divided by the proposed period, call it t again, plus some phase difference that accounts for the delay in time. And this will have, depending on how many terms they want, they've listed 3, 6, 8 terms here. AI, 2 pi, t, I. And what they'll do is calculate these AI from the records. Now it's done with a digital computer. For quite a long time it was done with a mechanical computer made of pulleys and springs, and styli. But in any case, they'll find all these coefficients, and then they'll produce using those coefficients the predicted tides based on where the moon and the sun are. That's all done for us by the National Ocean Survey. A couple other things that should be said about the tides. Because the moon, the rotation of the moon is about approximately 28 days. The tides typically go through a 14-day cycle. This is amplitude. Let's call this the mean tide level. First, there will be when the moon and sun are in phase and out of phase. There'll be what's called a spring tide. And gradually this will grow and this will shrink so that at some point, usually about 7 days after this, the strongest one, there will be tides where the two will have about the same height. This is called a neap tide. It's also spelled N-E-E-P. And the neap tide amplitude is lower. I didn't put in quite a scale. It's quite a bit lower than the spring tide. So in the spring tide you have a large tide range, and during a neap tide you have a smaller tide range. And this cycle, this goes through in a period of 14 days. So if you're doing modeling of estuarial hydraulics, it's a good idea to model it over a 14-day tidal cycle to get the effect of both the spring and neap tide. If you look down through this table, you can see how the highs and lows change. Also, you'll notice in there they have pictures of the moon, so you can see how the phase of the moon relates to the tide. You might figure out, just to get familiar with the tables, what the tide will be in Petaluma River on Saturday when we're there. I mentioned that the tides generate currents in an estuary. The currents are affected not only by the rise and fall of the tide and, of course, the resonances, but also by Coriolis force, just as we discussed earlier, which is important in broad bays. The South San Francisco Bay, for example, the current generally something like this. And it's common to have, well, the Dyer shows it here in an illustration in the handout. They have a circular path of current. The hydraulics of estuary is complicated by the fact that we typically have freshwater inflow here. Which has a density approximately 1.000. And seawater out here, which has a density of something like 1.025. Takes about 40 feet to make water to make a 1 foot difference in pressure between freshwater and seawater. That is, 41 feet of seawater, of freshwater will balance 40 feet of seawater. Doesn't sound like much difference, but it has a profound effect on the hydraulics of the system. The freshwater flowing out from the land, being less dense, flows over the salt water. And in fact, if in the mouth of Mississippi, where we have the small tide range that I mentioned earlier, we have let's say the Gulf out here, and it's a water surface. And if you measure the salinity of the water with depth, what you find is that there's something that looks like this, where this is saline and this is fresh. It's very pronounced in the Mississippi, and the reason is that there's a high freshwater flow and there's very little tide out here, so there's very little movement back and forth in the inlet. I should point out that the mouth of the Mississippi is a stream through a delta, so that it doesn't change in width much with distance. In any case, there's a very sharp front here. These fronts are observed where there's a little back and forth motion, and where the velocity of flow along here is not one that generates waves. And that velocity is when the Froude number, remember the Froude number? Is equal to u divided by the square root of gh. It's a ratio of the inertial forces to the wave forces. And here I'll put delta rho over rho, where the delta rho is the difference in density between the two, and rho is the average on one or the other. When this approaches 1, then 1 is, when it is 1, that's the velocity of a wave on the surface here. And when the current u is such that the Froude number, that densimetric Froude number is called. When the u is such that that number approaches 1, then waves form on the surface, and they're reinforced as they go along. That is, the current continually reinforces them, with the result that they break, and there's mixing across that interface. So that even when we have very small tide range, so there's not much back and forth motion, we do get mixing under that particular condition. The reason the back and forth motion causes mixing is because the roughness of the bed and the banks, that is the roughness of the boundary, generate mixing that mixes up through the system. So when you have a large tide range, then what you see instead of this kind of a circumstance is that if we plot the salinity, what we'll find is that for a very large tide range, the salinity profiles will look like, let's say this is 20 parts per thousand, and 10 parts per thousand, 1 part per thousand. That is, when you have strong mixing, you get something like this. This is associated with relatively small freshwater outflows and large tide range. And it results from the fact that the tide makes the water flow back and forth and causes vertical mixing. You also notice that when the boundary is rough, and when you have a rough boundary, anything that creates mixing will change that behavior. Well, this situation, depending on what it looks like, profoundly affects the transport of sediment in this region. And I'd like to start there on Monday. In the videotapes, did it show the Savannah data, Savannah River data? Do you remember seeing that? I'll bring some of it and show you on Monday and explain how this affects.
That's what parts per thousand? That's parts of what per thousand?
1 part salt, sea salt.
Is that backwards then? Wouldn't it be higher to the left?
Oh, I have. Yeah, this is river. Oh, I have it backwards there. Thank you. And this is sea.
And it's angled that way?
Oh,
It's angled like that?
Oh, I got it. I still don't have it.
Numbers backwards.
River has, see, I've got it backwards. Still have it backwards. Make it the same here. Sea, river. What's that?
Better.